Just a second. Let us see about group 15, everybody. The general nature of the group 15 elements is that nitrogen and phosphorus as nonmetals, arsenic, antimony are metalloids, while bismuth is metal. And atomic size increases down the group, okay, reasonably, where antimony and bismuth will have very close values. Otherwise, it is reasonably increasing. Volume and density also increases down the group. Bismuth would have relatively more volume than antimony and arsenic. Next, ionization enthalpy, if you notice, 2s2, 2p3. This is the general configuration. So, because it has a half-filled stability, generally group 15 elements will have more stability than 16 or 14. So, first ionization will always be nitrogen greater than oxygen greater than carbon, and that is followed by the other group elements. And first ionization varies this way towards bismuth. In second and third ionization, bismuth would have slightly more value than antimony. Got it? Next. Electron affinity wise, if you notice, because they have an half-fill stability, they are reluctant to accept an electron. In fact, if you recall nitrogen, beryllium, magnesium, and all inert gases, they will have positive electron gain enthalpy or negative electron affinity. The values goes like this. Nitrogen has -5 units in kilojoules per mole. And as you go towards bismuth, energy is released, and bismuth can relatively release around 105 kilojoules per mole energy. Clear? This is only group where electron affinity is constantly increasing down the group. Because in all other groups, electron affinity will decrease down the group. In this group, it will always increase. Clear? Electronegativity wise, if you notice, down the group, electronegativity will decrease, where antimony bismuth will have almost the same electronegativity. Melting point and boiling point has slight variation. As you go down the group here, you exchange arsenic and bismuth positions. We are expecting bismuth to have more melting point, but arsenic would have relatively more. It depends upon how many number of electrons are participating metallic bond. Arsenic, almost all the electrons participate in metallic bond, while bismuth, NH2 electrons will not participate in metallic bond due to lanthanoid contraction. That's why melting point is observed where arsenic is slightly better than antimony and bismuth. Boiling point wise, now you exchange antimony and bismuth. It has to do with the mass, molar mass, atomic mass, but again, bismuth will be slightly lesser than that of antimony. These two exceptions you should know. Bond energy wise, pp bond would be more than that of NN bond, then arsenic, arsenic, and antimony, antimony. Single bond formation in nitrogen and nitrogen will have repulsions because of the electrons present. It will have repulsions. Next, if you notice, nitrogen can form p-pi p-pi bonds with itself and with the smaller atoms like carbon, nitrogen, oxygen, etc. Okay, due to the large size and poor overlapping, p and others, p and other elements do not form p-pi p-pi bonds, but they form d-pi p-pi bonds with oxygen or carbon or nitrogen. So phosphorus and arsenic can form d-pi d-pi bonds with transition metals as well. So you'll notice that if this is metal, it will give a pair of electrons at the same time. It will make a synergic bonding as d-pi and d-pi. Okay. So d-pi d-pi bond is observed between phosphorus with phosphorus and arsenic with metals. Got it? Next, nitrogen cannot form d-pi d-pi bonds because of its absence of d orbitals. Next, The catenation power of these elements is lesser than group 14 elements due to its bond dissociation energy. And moreover, if you check out the catenating power, phosphorus would have relatively better than nitrogen, and you can see it comes with a single bond character. Single bond character wise, PP is more stable. That's why it will have better catenating property than NN, than arsenic, and then antimony. And nitrogen has very less tendency to form single bonds with NN bonds because of it. It can form a much stronger multiple double bonds. Okay, so multiple double and triple bonds. So nitrogen, instead of just existing in a single bond, it will exhibit more of a double bond or a triple bond character. That's why it cannot have a lot of catenating nature. While phosphorus, antimony, and bismuth, they will have, they are tetraatomic in species. So that means they'll exist in the form of P4, ACE4, and so on. Clear? And they can catenate relatively better. Next. Oxidation states wise, if you notice, the common oxidation state observed is -3, +3, and +5. Nitrogen exhibits anywhere from -3 to +5. You can notice NH3 has -3, N2H4 -2, hydroxylamine -1, hydrozoic zoic acid N3H -half, 1/3, N2O +1, +2, +3, +4, +5. So you can notice a lot of them have, all different oxidation states are observed for nitrogen. When it comes to phosphorus, phosphorus shows -3, -2, +1, +3, and exceptionally only one compound shows +4, and +5 usually exist. Got it? So remember, only one compound of phosphorus shows +4. Okay. Hydrozoic acid, in case if you need to check out what is its structure and what is its oxidation state, the structure is this way: N3H. The central nitrogen has sp hybridization, side nitrogen has sp2, and the right side one has sp. Okay. Removing of H plus, it will give a resonating structure within the molecule known as azide. The ion name is azide. It's a linear molecule. What you will notice is the stability of -3 oxidation state down the group, you know, uh, uh, decreases, okay, due to increase in the size, due to increase in size, okay, and in metallic nature. As you go down the group, -3 oxidation state will decrease. And stability of +5 oxidation state decreases and +3 increases down the group due to lanthanoid contraction. Okay, this is due to lanthanoid contraction effect on bismuth. So you notice that bismuth shows +5 oxidation state only with oxygen and fluorine, and +5 acts as an oxidizing agent, strong oxidizing agent. In fact, as per NCRT, Bi2O5 does not exist only. Right? Clear? That means it is highly unstable. It will immediately convert into Bi+3. Oxidation state between +1 and +4 for nitrogen undergoes disproportionation, which means if nitrogen holds +1, +2, +3, or +4 oxidation state, it will undergo disproportionation. For example, if you take HNO2, HNO2 has +3 oxidation state. It will undergo disproportionation into HNO3 plus NO2. Okay. It is not just in this, in any particular form also. For example, if you have NO2 in basic medium, correct? Most of the compounds in basic medium will change. Here oxidation state is +4 in basic medium. So imagine in aqueous form here. So it is as if first it is becoming HNO2. Okay. And HNO2 is a mix, NO2 is a mixed oxide. So first it will become NO2 minus HNO2 plus HNO3. Clear? And since it is in basic medium, This H plus won't be there, and it will become NO2 minus and NO3 minus. So what is the oxidation state now? Now here it is plus 3 and here it is plus 5. What happened? So NO2 has undergone disproportionation into plus 3 and plus 5. Okay. Disproportionation is an important reaction, everybody. Remember, NO2 will always undergo disproportionation into NO3 minus, NO2 minus, and NO3 minus. Right? Here also, as an acid also, if you notice, HNO2 from plus 3 it is converting into plus 5 and plus 2. So that is also undergoing disproportionation. All the intermediate oxidation state for phosphorus, disproportionation takes place both in alkaline and acidic medium to give products of plus 5 and minus 3. Exclusively when it comes to phosphorus, what you would notice is that they eventually become plus 5 and minus 3. The disproportionation eventually becomes plus 5 and minus 3. For example, if I take HPO3 2 minus, oxidation state here is plus 3. Okay. In acidic medium, first it will become H3PO3. That as you start heating a bit, it will convert into plus 5 and minus 3. Okay. Check out P4. P4 has zero oxidation state. In basic medium, it will become plus 1 and minus 3. And this plus 1 will again undergo disproportionation. Okay. If you again add some acid, again add some acidic medium, keep it in acidic medium, it will become H3PO2, which will again disproportionate into PH3 and H3PO3. Correct? So that will keep on happening till you always get plus 5 and minus 3. Okay. So remember, P4 undergoes disproportionation, H3PO3 get disproportionation, H3PO2 get disproportionation. So all these compounds get done. Plus 3 oxidation state of bismuth, antimony, arsenic are stable with respect to disproportionation. Okay. So when they are plus 3, you will not find much of disproportionation for bismuth, antimony, and arsenic. So I hope all of you understood the general fundamentals. Next, check out hydrides. When it comes to these elements, group 15 elements, as much as nitrogen is concerned, there are three major hydrides which you will observe: NH3, N2H4, and N3H. While N3H is acidic, the other two are basic in nature. Phosphorus has pH3 and P2H4. Okay. Both of them are neutral and very less basic in nature. At least in aqueous solutions, they are neutral. Got it? Next. In case if you notice that the formation of NH3 is negative, Born-Haber process, while the formation of these three are positive. Okay. That is, if I take N2 plus 3H2 becoming 2NH3, the energy is released. While P4 plus H2 to form PH3, the energy is absorbed. So in these three cases, energy is absorbed. With ammonia, energy is released. Secondly, except for ammonia, all others are not hybridized. So you need to remember that PH3, ASH3, SBH3, and BiH3 are unhybridized. They are unhybridized groups. Okay. Next one is bond dissociation energy. Because it has come from an hybridized orbital, the overlapping would be very, the overlapping will make it very strong. The stability of the bond will be high. While these have very weak overlapping because they are unhybridized. So down the group, bond dissociation energy decreases. Because the bond is weaker, it can be used as a better reducing agent. So therefore, down the group, reducing nature will increase. And the same logic can be explained for thermal stability also. Down the group, thermal stability decreases. Boiling point wise, ammonia will have certain amount of hydrogen bonding, because of which it will not be at the end. It will come somewhere between. So bismuth will have first based on the molar mass. then antimony, then it is supposed to be arsenic, but before that we will get ammonia due to its hydrogen bond. Okay, so then comes ASH3 and then PH3. Next is bond angle. Ammonia would have relatively higher bond angle than PH3, then ASH3, antimony, and bismuth. So down the group, as you go, bond angle will always decrease. Basic nature is also the same. Here in ammonia, the lone pair is present in the sp3 hybridized orbital. So it is more directional, it is more easy to give. But as you go down the group, metallic character increases, so the ability to donate electrons will decrease. Got it? That means, sorry, it is more dispersed. The cloud is more dispersed, so it will not be a concentrated lone pair kind of a degree. Okay. So you can see these four do not form salts with aqueous solution because they are less basic. In fact, their basicity is lesser than water. So ammonia is more basic than water and water is more basic than pH3 in aqueous solution. So pH3 in aqueous solution doesn't do anything. It will remain pH3 only. And water itself will act like a base, takes H plus and becomes H3O plus and Cl minus. Okay. While if you had that in HI anhydrous, if you take it in an anhydrous form, then pH3 will become pH4 plus and I minus. In anhydrous form, this is what you will notice. Close. Next, you can notice oxides. There are two types of oxides this group shows, mainly A2O3 and A2O5. N2O3 and P2O3. P2O3 will also exist as a dimer, which is P4O6. They show acidic character. Arsenic, As2O3, As2O4, and antimony, Sb4O6. These will show amphoteric nature, while bismuth will show basic character. While N2O5 onwards, antimony, these are all acidic. Bi2O5 is amphoteric. Halides wise, if you notice, NF3, NCl3, NBr3, and Ni3. Out of these three are explosive in nature. Okay. That means if they come in contact with water, they explode. NF3 is relatively more stable. Okay. Next, N2 plus X2 is giving NX3. That is an reaction, a redox reaction where energy is released. Okay. Next, if you notice, phosphorus can show all of these halides. Arsenic can show all of these halides. Antimony can show all of these halides. Bismuth does show all of these halides, but BiF3 is completely ionic. The rest all are covalent compounds. Again, a very important question. Out of all of these compounds, how many are ionic, how many are covalent? All of them are covalent except for BiF3. I guess this part is clear, everybody. Right. Now, when it comes to EX5, nitrogen, because it does not have an empty d orbital, it does not show any NX5 kind of cases. Phosphorus shows with uh, fluorine, chlorine, and bromine, not with iodine. Arsenic will only show with fluorine. With chlorine, it is less stable. Antimony shows with fluorine and chlorine. Bismuth shows only with fluorine, and it is covalent. Okay. In fact, PI5 is extremely unstable. It will convert into PI3 plus I2. Basic nature, if you notice, okay, NF3 will have a strong inductive effect. Why? Withdrawing electrons. Because of which its basic character will be weak. Ni3's basic character is high. In general, if you compare the basic character, down the group, the basic character will always decrease. Okay. Here, electron density, because of its electron negativity, will hold better. So nitrogen is always better basic than phosphorus, arsenic. antimony and bismuth in all the cases, whether it is in the form of hydrides, halides, or oxides. Got it? Next, NBr3, Ni3, correct? They exist only as ammoniates. Otherwise, they are explosive. That is NBr3 dot NH3 or Ni3 dot NH3, like this, as an ammonites. Otherwise, if they come in contact with air or water, they will explode. See, what is the part of hydrolysis for these compounds? Okay. If we take NF3, at normal conditions, it does not undergo hydrolysis. If you take NCl3, in NCl3, you would notice that water will not attack nitrogen, rather it will attack chlorine because nitrogen does not have an empty orbital. So what do we get? Water will attack chlorine. This will become N minus. N minus will take H plus. So you will get ammonia and chlorides will become HOCl. Got it? Chlorides will become HOCl. Next, PF3 hydrolyzes slowly, while PCl3 hydrolyzes reasonably. Here, water attacks phosphorus directly, not chlorine, because phosphorus has empty orbital and has high delta positive charge. Therefore, all three chlorines will be replaced here to give phosphorus acid. So basically, POH thrice will always undergo tautomerism to form H3PO3 and HCl will be formed here. Okay. So it is a slow step. Breaking of PX bond is observed. Next, basic nature. If you notice, PI3 will be more basic than PBr3, PCl3, and PF3. It is to do with the inductive effect. Okay. If you recall the other day, there was a question asked like how many moles of NaOH are required for hydrolyzing, completely neutralizing PCl3 in water. In PCl3 in water means you will notice that one phosphoric acid will have two acidic hydrogens, and here we have three acidic hydrogens. So total 5 moles of NaOH is required to neutralize 1 mole of PCl3. Okay. Next, notice the reaction with metals. These elements react with electropositive metals to form compounds with -3 oxidation state. Magnesium nitrate, magnesium bismuth, lithium nitrite, calcium phosphide, sodium arsite, okay, zinc antimonite. So this way, these are various types of uh, uh, reactions that are observed with metals. What we studied so far are the general properties of group 15. And if you notice for mains, that is how much it is been asked. Now let's talk about the compounds one by one, starting with dinitrogen. Preparation of N2. N2 is commercially prepared by liquefaction and then distillation of air. Liquid nitrogen distills first, then O2. Okay. Lab preparation is, it is prepared by treating NH4Cl plus NaNO2. Very important reaction. See, NH4Cl plus NaNO2 will convert these two nitrogens into N2 and makes this as NaCl and rest will be H2O. Okay. This nitrogen is getting oxidized, this nitrogen is getting reduced. Okay. During this, there is a small amount of NO and HNO3 also being formed. Okay. And this we can remove it off with K2Cr2O7. Okay. Because if you notice NO will get oxidized to HNO3 again. So we'll get small quantity of HNO3 and rest of the nitrogen will come out as pure. Correct. So you can see the byproducts NO HNO3 can be removed out by passing the mixture through aqueous H2SO4 containing K2Cr2O7. Typically heating of salts. See, ammonium salts on heating will also give you N2. If it is chromate, you'll get N2 plus Cr2O3 and H2. What are the other compounds which will give? Check out. Anything which is oxidizing anions, like Cr2O7 2 minus has an oxidizing property, NO2 minus, NO3 minus, MnO4 minus, MnO2 minus, ClO3 minus. These all will have oxidizing property. While compounds which anions which does not have oxidizing property includes sulfate, phosphate, chlorates, chloride, bromide, iodide, oxalate. All of these will give you NH3. Got it? So if you are heating these ammonium salts, then you will get ammonia. NH4 and NO2 on heating will also give you N2. Similarly, heating azides. Azides will be relatively very pure because they do not have any other impurities coming out. Barium azide, sodium azide on heating will become barium and sodium will get reduced. Azide will convert into N2 gas. Urea in NaNO2 disonium salt formation, if you recall, both sides disonium salt will form, N2 gas will come out, and this molecule will convert into acid. Clear with that, everybody? Check. Next is by oxidation of ammonia. Ammonia, when you react with CuO and heat, copper will get reduced and ammonia will convert into N2. Okay. Now, what are the reactions of N2? Well, N2 has extremely high, bond dissociation energy, some 917 kilojoules per mole, so which is very high value. So it's very difficult to break N2, therefore it is very less reactive. So N2, CO, Cn minus, all of them have same bond order. Okay. Carbon monoxide and Cn minus are relatively much more reactive because of their polar nature and antibonding character of homo orbitons. While N2, in case of lithium, magnesium, nitrogen, these are all the products which you can get. So first two cases you will get nitrate. Next one is Born-Haber process. With boron and aluminum also it will get nitrites. Al2O3, Cl and N2 will also give you Aln plus CO. Okay. N2 and O2 only in the presence of electrical arc, okay, and strong heating, then you will get NO gas. Otherwise, in air, nitrogen and oxygen are, inert to each other. Yeah. Next compound we need to explore is ammonia. Okay. We can get ammonia from ammonium salts, but they have to be non-oxidizing salts, okay, like chlorides, sulfates, phosphites, and so on. Now you notice that ammonium chloride with NaOH on heating will give you ammonia plus NaCl and H2O. And ammonium sulfate plus calcium hydroxide will give you ammonia plus calcium sulfate plus H2O. Next, reduction of nitrites and nitrates. If you notice NaNO2 with zinc and OH minus will get NH3 and Na2ZnO2. And NaNO3 in zinc and hydroxide will give you NH3 and NaNO2 plus half O2. So basically here zinc will act as a very good reducing agent and convert any oxidation state of nitrogen into NH3. Nitrites. If you take nitrates just on hydrolysis, they'll give you ammonia and rest will become hydroxide. Okay. Next, ammonium salt of non-oxidizing. Just now we have discussed ammonium chloride, sulfate, phosphates. They all will give you ammonia. Next, urea. Hydrolysis of urea also. If you, instead of reacting with HNO2 directly, if you hydrolyze it, you'll get urea. 2 moles of NH3 and CO2. Okay. Next, formation of calcium cyanamide. This we discussed the other day also. Calcium oxide plus carbon will give you calcium carbide plus carbon monoxide. Calcium carbide, when you react with nitrogen, will become a mixture known as nitrolim. Calcium cyanamide, this is CaNCN plus C. This is also called nitrolim mixture. Structure of calcium cyanamide is like this, calcium 2 plus and this. And if you react with water, this part will get H2O first. And further hydrolysis, cyanides will convert into acids. Okay. Cyanides will convert into acids and ammonia gas is released. And if you further hydrolyze this one, you will get this nitrogen converting into ammonia and this will converting into carbon dioxide. And if you react with calcium carbonate, it will convert into calcium hydroxide, it will convert into calcium carbonate. So basically, calcium cyanamide on hydrolysis, you can stop at urea, here, or you can make further hydrolysis to give, ammonia and CO2. Okay. Next, Born-Haber process is N2 plus 3H2 giving 2NH3. Delta H is negative for that. You require high pressure and reasonable temperature. Not very high temperature because reaction might again go backward direction. Catalyst is used, the latest catalyst that is used is K2O in the presence of Al2O3. Okay. And some amount of Fe2O3. Old catalyst, that means in the old books, if you notice, the catalyst used was iron. So if the question is asked, can iron be used as a catalyst? Answer is yes. Okay. So while the latest catalyst that is used is this one. Okay, molybdenum used to act like a promoter in the case of iron. What are the properties of ammonia? It is colorless, pungent, and pungent smelling gas. It will showcase hydrogen bonding in liquid and solid state and highly soluble in water due to its intermolecular hydrogen bonding. Okay. It will react with O2, right, and gives a yellow color flame. Ammonia with O2 gives N2 gas with a yellow color flame. It reacts with chlorine. This reaction is very important, everybody. Check this out. There are two ways you can react. Either you take excess of ammonia. If excess of ammonia plus Cl2 is been added, that is 8 moles of NH3 plus 3 moles of Cl2. It will convert into N2 and rest will convert into ammonium chloride. This is when you have ammonia in excess. Okay. See, the reaction goes something like this. Ammonia plus Cl2 will become N2 plus NH4Cl. Okay. Next, 2 moles of ammonia plus 3 moles of Cl2 will give you N2 plus 6 moles of HCl. Okay. And this 6 moles of, this is the first reaction. 2 moles of NH3 plus 3 moles of Cl2 will become N2 plus 6 moles of HCl. And this 6 moles of HCl and 6 moles of ammonia will convert into ammonium chloride because more like an acid-base reaction. So that's why this reaction, 8 moles and 3 moles converting into 1 mole and 6 moles of ammonium chloride. What if Cl2 is excess? Ammonia with excess of Cl2. So 2 moles of ammonia plus 6 moles of Cl2 will form 2 moles of NCl3 plus 6 moles of HCl. So here you will see more of HCl present. So NH3 plus Cl2 will give you N2 plus HCl and N2 plus 3Cl2 will also give you 2 moles of NCl3. So if I add both of them, I'll get 2 moles of NH3 plus 6 moles of Cl2 gives 2 moles of NCl3 plus 6 moles of HCl. Okay. What happens with excess ammonia and what happens with excess chlorine? One second. Yeah. Next. Reaction with bleaching powder. Ammonia, when you react with bleaching powder, COCl2 will convert into N2 plus CaCl2 plus H2O. Next is precipitation reaction with NH4OH. See, NH4OH plus NH4Cl, correct? This is the reagent that we can use to precipitate aluminium, chromium, and iron. This we will learn in salt analysis again. So Al plus 3, Cr plus 3, and Fe plus 3 all will get precipitated in the presence of NH4OH and NH4Cl. HgCl2 and Hg2Cl2 will also form precipitates. If you take Hg plus 2, it will become a white PPT, HgNH2 and Cl. If it is Hg2Cl2, it will become HgNH2Cl plus Hg, which is a black PPT. Next, you see, moist ammonia should not be dried using these compounds, H2SO4, P4O10, or CaCl2. For first two for the obvious reasons because they are acidic. H2SO4 is acidic, P4O10 is acidic. So ammonia with these acidic compounds, right, will be uh, making an acid-base reaction. While CaCl2, although it is basic, correct, when you take CaCl2, it will form a complex with ammonia. That is, it will form CaCl2 dot 8NH3. So to avoid this complex formation, you do not use calcium chloride. Instead, we can use calcium oxide, which is completely basic and it will absorb water and it will not have any reactivity directly with ammonia. Got it? So you can notice that here with H2SO4, you will have this P4, it will form this. With CaCl2, it will form NH4Cl, or like I said, it will form a complex CaCl2 dot 8NH3. Next, hydrazine. Hydrazine is only for advanced, and that too, they have deleted it as such, that is not directly asked. But nevertheless, I'll just show you few important reactions, how that is working out. Okay. It is done by Ratching's process in which ammonia is oxidized with dilute solution of NaOCl and CaCO. So ammonia, when you react with this compound, NaOCl or CaOCl2, it will give N2H4. Okay. And rest sodium or calcium will form the respective chlorides. Okay. So NH3 plus NaOCl is a fast reaction to give NH2Cl. Next, NH2Cl plus ammonia, which is a slow reaction, will convert into N2H4 and HCl. So side reaction is NH2Cl plus hydrazine will try to form N2 and NH4Cl. Correct? A small composition of N2 will keep coming. If, if you do not control the reaction, the side reaction will be catalyzed in the presence of heavy metal ions. To prevent this reaction, okay, continuous distillation is to be done, okay, using little amount of glue or gelatin which masks the metal ions if any present. Hydrogen is colorless liquid which smells like ammonia. It readily reacts with air and produces high amount of energy, okay, so it will convert into N2 and H2O, highly exothermic. In aqueous medium, it acts like a strong reducing agent. So N2H4 plus I2 will easily convert into N2 and HI. With O2 also same logic. With MnO4 minus also same logic, Mn plus 2 and N2. It reduces less electropositive elements like copper 2 plus this and this into metals. Okay. And N2H4 in zinc and HCl will convert into ammonia. Okay. Right. Next, oxo acids of nitrogen. There are mainly three oxo acids we need to address. One is hyponitrous acid, which is H2, N2, and O2, where nitrogen has a double bond with OH and OH here. Okay. and it can exist on the syn type on an anti-type. This is hyponitrous acid. Next one is nitrous acid, HNO3, oxidation state is +3. Next one is nitric acid, HNO3, oxidation state is +5. Okay. Last one is per-nitric acid, where same nitric acid also has a peroxy linkage. Now, H2N2O2 is relatively stable, right, at low temperature. Okay. That is, as the temperature increases, this will easily convert into H2O plus N2O. But it does not mean if you take N2O and water, you add water, the reverse reaction is happening. No. Therefore, it is not an acidic oxide. In fact, N2O is a neutral oxide. There are only four neutral oxides in periodic table: H2O, CO, N2O, and NO. Right? These are the four neutral oxides. So just by adding water, you will not be able to get, uh, this acid per, sorry, hyponitrous acid. Next, N2O5, when you add it to water, it will become HNO3, and while NO2 will become HNO2 and HNO3. So notice N2O5 is called as anhydride of HNO3, while NO2 is called the mixed anhydride because it is not giving one acid, it is giving two acids. So that's why it is called mixed anhydride. Okay. Next, nitrous acid. Again, this is only for JEE Advanced. The two, I mean, in the recent times they have not asked much, but just we'll see a basic preparation here. So HNO2 is stable only in dilute solution. It can be prepared by acidification of barium nitride in cold dilute H2SO4. So if you take cold dilute H2SO4, barium will convert into precipitate and this will convert into HNO2. N2O3 also, when you add it to water, will give HNO3. HNO2 is a weak acid. When you add it with NaOH, will become NaNO2 plus H2O. HNO2 will disproportionate on its own to form HNO3 and NO. It can be treated as both oxidizing as well as reducing agent. Okay. So if you remove HO2 out of this, that means protonate here, protonate this one, H2 plus, and it will convert into an NO plus. And if you take an electron, it will become NO. So that means when it is acting like an oxidizing agent, it will accept an NO and electron and convert into NO. And that is a reaction you will notice here. When HNO2 is treated with S2 minus, I minus, Fe plus 2, cobalt plus 2, SO2, and Sn plus 2. These are all reducing agents, and HNO2 is oxidizing agent. So the product of HNO2 is always NO, 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 and NO. But rest all are undergoing various oxidations. Sulfur will always convert into colloidal sulfur. Iodine will to minus, I2, and iron plus 2 to plus 3, cobalt plus 2 to plus 3, SO2 to H2SO4, and Sn plus 2 to Sn plus 4. While if HNO2 undergoes oxidation, it will convert itself into HNO3, which means here it is acting like a reducing agent. KMNO4, K2Cr27, peroxide, Cl2. These are powerful oxidizing agents. If you add HNO2 to them, it will get oxidized to HNO3 and rest will get reduced. Next, notice nitric acid, HNO3 preparation. First is Birkeland-Eyde process. N2 plus O2 is giving NO gas, and that is only going to happen in electrical arc. And if NO gas is added to subsequent amount of O2, we will get NO2. Next, NO2, when you add it to H2O, will get HNO2 and HNO3. HNO2 will again decompose to get HNO3 plus NO. And this NO is again recycled back into the second step. Okay. So net reaction is N2 plus O2 plus HNO3 is giving HNO3. Clear? So you can see these are the following steps which we discussed already. Next. Mm. Oswald's process. Ammonia plus O2 will give you, you know, in the presence of platinum or rhodium, will convert into NO and H2O. NO plus O2 will give you NO2 again. NO2 plus H2O will become HNO3 and HNO2. And HNO2 will become HNO3 and NO. So that cycle will keep continuing. Aqueous HNO3 on distillation product produces an azeotropic mixture which is 68% HNO3 by mass. HNO3 is further concentrated by treating it with concentrated H2SO4. Okay, and it gives 98%. It gives 98% of HNO3. Okay, done everybody. Next, check. Pure HNO3 is colorless liquid, and on long standing, it appears to be yellowish brown due to its decomposition in presence of light. I told you about that. It will convert into NO2 and O2, and it will give yellow color gas, yellow coloration in the flame. HNO3 acts as oxidizing agent, okay, in very dilute, and concentrated solutions. Okay, with increasing concentration, the oxidizing power will start increasing, which means concentrated 60% and above is the strongest oxidizing agent. Sorry. See, when we use concentrated HNO3, what will happen? When we are using concentrated HNO3, it oxidizes metals into higher oxidation state and itself get reduced into NO2. So HNO3 will be reduced to NO2, giving nascent oxygens. These nascent oxygens, when metals react, they'll convert into their respective oxides. So M2OX plus HNO3 will give you metal nitrates and H2. Okay. So you'll notice that M plus HNO3 will convert into metal nitrates plus H2O and NO2. This is the overall reaction that will take place. So what are all the metals that will happen here? Mercury, zinc, copper, lead, silver. All of this will be dissolved easily in concentrated HNO3 and convert them into nitrates, NO2. Next, metalloids are oxidized to acids. Okay, check. For example, tin, arsenic, antimony, they are metalloid in nature. They will be oxidized to their respective acids. Unlike in the above metals, they are converting into their nitrates. Here they will convert into acids. So H2SnO3, H3SO4, H3SbO4. The rest of the part is the same, NO2 plus H2O. While beryllium, aluminium, chromium, iron, cobalt, nickel, okay, important elements, they become passive with concentrated HNO3 due to the formation of a thin oxide layer on the surface. Okay, integer type question, please remember this. So beryllium, aluminium, chromium, iron, cobalt, nickel, they will be passive towards concentrated HNO3. Noble metals like gold, platinum, rhodium, as well as iridium, they too cannot be attacked only by concentrated HNO3. They will be dissolved if it is present in the form of aqua regia. Aqua regia is these two concentrations in the form of in the ratio of 1:3. Okay. Next, due to little oxidation of these will form complexes with concentrated HCl. Hence, the oxidation state of gold and platinum is favored in the forward direction. So, how it works with aqua regia, written it here. Sorry. See, HNO3 plus HCl will form NOCl plus H2O plus Cl2. Okay. And gold plus HNO3 plus HCl will give you this complex HAuCl4 and NO gas will be released. Same with platinum, HPTCl6 platinic acid plus NO gas will be released. That's how it will get oxidized. Next, aqua regia appears to be yellow due to the formation of NOCl. Okay. Next, if you notice dilute HNO3, metals react with dilute HNO3 to produce metal nitrates. And if the metal is above hydrogen in electrochemical series, okay, then N2O is produced, out of which only two exceptions are there. In case of lead, instead of giving N2O, it will give NO. In case of tin, instead of giving N2O, it is give ammonium nitrate. Only these two are exceptions. Now you see, these all will have negative reduction potential. Zinc, iron, lead, tin, nickel, chromium, copper, nickel, chromium, cobalt, all of them will have negative reduction potential. They all are supposed to give N2O, but out of that, two exceptions are there. Lead, instead of giving N2O, it will give only NO, and tin will give you ammonium nitrate. And if the metal is below the reduction series, which means the reduction potential is positive, then reduction potential is positive, then you can notice that copper, silver, mercury, it will react with dilute HNO3, will convert into respective nitrates plus NO and H2O. Okay, so they will only give NO gas, not N2O. Okay, next, with very dilute. With very dilute, NH4NO3 is only formed for all the metals except for magnesium and manganese, which gives H2 gas. So aluminium dissolves, iron dissolves, zinc dissolves, manganese and mercury, they will not get dissolved the ammonium form, so they'll get only H2 gas. Then, if you quickly recall about the uh, reactions of nitric acid, concentrated nitric acid with toluene will give you you know uh, TNT, clear, trinitro toluene. With next, with phenol it will give quinolone. uh, with simple cyclohexyl alcohol will give you this double bond of constant HNO3 will open up this bracket and converting into adipic acid. Cellulose will converting into cellulose nitrate. Then see the reactions with non-metals. Carbon with concentrated HNO3 will convert into CO2 plus H2O plus NO2. Phosphorus will convert into its highest oxidation state, which is P4O10, okay, in the form of H3PO4. Next, S8 plus concentrated HNO3 will convert into H2SO4. I2 will convert into HiO3. Okay, not HiO4. Remember, it will convert into iodic acid, not periodic acid. Okay, these four are very strongly asked in exams, so learn it. Carbon, phosphorus, sulfur, and iodine. What are the products that will give? Next, oxidation of these compounds. S2 minus will oxidize to sulfur, I minus to I2, Fe plus 2 to plus 3, tin to plus 4, oxalate to carbon dioxide, sulfate to SO4 2 minus. That's it. These are the oxidations of those other compounds. Clear? Next, let us discuss oxides of nitrogen. Nitrous oxide, N2O, okay, or dinitrogen monoxide. Ammonium nitrate on heating, correct? It will become N2O plus H2. Zinc, when you treat with dilute HNO3, just now we have seen that it will become N2O and zinc nitrate. NH2OH, when you treat with NaNO2, will convert into N2O, NaCl, and H2O. It is neutral, colorless, diamagnetic gas. Structurally, this is how we write it down. Nitrogen is the central atom, and these two are the canonical structures of that. Next is nitric oxide, also known as nitrogen monoxide. Copper plus dilute HNO3 will give NO. Oswald's process will give NO. Birkeland-Wright process will give NO. So nitric oxide can be purified by passing the mixture of acid through aqueous FeSO4. The brown ring formed is unstable on heating, and shaking it again releases NO gas. It is a paramagnetic compound. It is neutral and also colorless. Structurally, it will have N double bond O with minus and plus charge on nitrogen and oxygen. The bond order in this case is 2.5. Okay, bond order is 2.5 in the case of NO, and it is going to form a loose dimer at low temperature. That is NO, right? Selects from both ends, so we'll get this as NO at low temperature. Next one is nitrogen sesic oxide, which is nitrogen trioxide, N2O3. If you take NO, react with NO2 or N2O4, you'll get N2O3. It's a blue color solid. Important, it is blue color solid. It is acidic in nature, and N2O3 on hydrolysis will give HNO3. So we can say that N2O3 is the anhydride of HNO2. Structurally, you will notice that it will convert into this form, N2O3. This is the stable form. Another isomeric form which it can exist is this one. So we can have NN bond as well as NON bonds. Both can exist. And in solid state, okay, in solid state, it appears N2O3 will appear like NO plus and NO2 minus. This is how it will appear, NO plus and NO2 minus. Okay. Here everyone. Right. Next, you see nitrogen dioxide, NO2. Lead nitrate on heating will become PbO plus NO2. Concentrated copper in concentrated HNO3 will convert into copper nitrate plus NO2. NO plus O2 will convert into NO2. This is all about getting NO2. Structurally, NO2 will have, uh, you know, a single electron because octet is incomplete in this case. It is a reddish brown color gas. It is paramagnetic in nature. Non-delocalized electron undergoes dimerization. So this electron does not undergo delocalization. So therefore, it will easily undergo dimerization. So it is colorless, diamagnetic, and liquid or solid state. Which one? I'm talking about N2O4. Okay. And when it comes to solid state, it will exist as NO plus and NO3 minus. It will exist as NO plus and NO3 minus. And liquid N2O4 is used as a non-aqueous solvent and can be used to prepare anhydrous metal nitrates. Okay. So you can notice ZnCl2 plus 2 moles of N2O4 as a solvent. It will convert into zinc nitrate and NOCl. NO2 plus F2 will convert into NO2F, and same is the case with Cl2. And NO2 and XF2, which is fluorinating agents, will fluorinate that into NO2 plus F, and xenon will get reduced. If it is NO plus Cl2, it will become NOCl. So NO plus F2, it will become NOF. If it is NO2Cl, NO2 plus Cl2, it will become NO2Cl. And next, NO plus XeF2, that is NOF, and Xe will get reduced. Lastly, you will notice nitrogen pentoxide, HNO3. HNO3, when you treat with P4O10, right, it will get completely dehydrated into N2O5. And metaphosphoric acid, HPO3 is formed. You know that phosphoric acid, when you use P4O10, will always get metaphosphoric acid. Okay. So these are the solid state compounds, guys. N2O3 as NO plus and NO3 minus, N2O4 as NO plus and NO3 minus, N2O5 as NO2 plus and NO3 minus. N2O5 is a diamagnetic colorless gas. N2O5 reacts with sodium, will convert into NaNO3 and NO2. Everybody clear on that? Let me just give you an introduction towards the allotropes of phosphorus. Okay. And later today or tomorrow, we'll discuss all the reactions of phosphorus. Okay. See, what are the allotropes of phosphorus? First, it is mainly it has white and red. Other than that, it has black and scarlet also. So it is a strained molecule. P4 will have an sp3 hybridization on every phosphorus with a bond angle of close to 60 degrees, highly strained, highly reactive, insoluble in water and but soluble in CS2. Okay. It readily catches fire. P4O10 will give you a white dense fume. It is stored in H2O. Okay. Sorry, it is a poisonous solid. It glows in dark, which we call it as chemiluminescence or phosphorescence. Okay. Next, red phosphorus. If you take white phosphorus and heat it at around 573 kelvins, for many days, it will convert into red phosphorus. Red phosphorus is polymeric. P4 unit joints means P4 has been joined in all the units. So you can see P4 here. Check out. Now you will notice a polymeric chain between this phosphorus and phosphorus. Clear? And that's how this will remain as sp3 hybridized yet, but it will remain sp3 hybridized in all the phosphorus positions. It is definitely less reactive than white. It does not catch fire. It reacts with O2 on heating. It is insoluble in water as well as CS2. It is non-poisonous and does not glow in dark. Black. This is thermodynamically more stable phosphorus. It is also polymeric and layer-like structure. Red phosphorus, if you heat it around 800 kelvins, it will give alpha black. If white phosphorus is directly heated, you will get beta black. Okay. Alpha and beta are different in terms of their structures. One is ABAB, the other one is ABC type of form. If you heat white phosphorus strongly over 800 kelvins, it will convert into P2 gas. Okay. Bond order here is also 3, diamagnetic, but it is extremely unstable at low pressures. So I hope all of you got an idea about what are the compounds which you need to learn. Okay. So, 1 second.